All right, so today we're going to jump into a really cool scientific detective story. It's all about a revolutionary material, a series of experiments that were just baffling, and a massive discovery that was hiding in, of all places, the middle of a simple flame. Let's start with the big puzzle. So here's the question that researchers at Washington University were wrestling with. How in the world do you use fire to create one of the most amazing materials ever discovered, carbon nanotubes? I mean, fire is usually pretty good at destroying things, right? Not building them with microscopic precision. So how'd they do it? First things first, though, to really appreciate this breakthrough, you have to understand what they were after and why it's been such a massive challenge for so long. We are talking about single-walled carbon nanotubes, SWCNTs for short. Just picture this. You take a sheet of carbon that's only 1 atom thick, that stuff is called graphene, and you roll it up into a perfectly tiny, seamless tube. What you get is a material that is ridiculously strong, way lighter than aluminum, and an even better conductor of electricity than copper. Seriously, the possibilities are straight out of science fiction. But, and this is a huge but, making these things has always been a nightmare. For decades, the process has been crazy expensive, super inefficient, and it usually makes a whole lot of gunk, like soot, that you don't want. The real kicker? Trying to make enough of it for actual, real-world products? That's been the roadblock holding back a whole technological revolution. Okay, this is where the story gets really interesting. The researchers had this idea to use a flame to grow the nanotubes. I mean, it makes sense. Flame synthesis is already used to make things like carbon black for tires on a huge scale. They just had to figure out the perfect recipe. So they built this really clever setup called an inverse flame. Now, normally, fuel comes out of a jet in the middle and air is on the outside. They flipped that. Air in the middle, fuel on the outside. This gives them incredible control over the flame's chemistry, letting them create this perfect little zone for growing nanotubes without all that nasty soot. And the secret ingredient? Tiny little particles of iron that act as a catalyst. And this is where the mystery starts. They ran experiments with 3 flames, we'll call them A, B, and C, that were, for all intents and purposes, identical. But just look at these results. Flames A and C produced basically nothing. But flame B, it went absolutely nuts, churning out a huge amount of really high-quality nanotubes. This was the million-dollar question. The temperature was the same, the fuel was the same, the setup was the same. So what was the hidden variable? What on earth was Flame B's secret? The hunt was on. The researchers had a pretty strong hunch. They suspected the answer wasn't really in the flame itself, but in how that flame was messing with their secret ingredient, that iron catalyst. Their main theory was that the tiny little differences between the flames were actually changing the chemical state of the iron. So it wasn't about the heat of the flame, it was about its chemistry. How much oxygen was available to react with those iron particles. And this gets right to the heart of it. In flame A, there was just a little too much oxygen. So what happened? The iron catalyst basically started to rust. It got highly oxidized. Flame C was the total opposite. Not enough oxygen, so the catalyst just stayed as pretty much pure iron, or what chemists call reduced. And that's what led them to the Goldilocks hypothesis. If flame A's catalyst was too oxidized and flame C's was too reduced, maybe, just maybe, flame B was the perfect sweet spot, the one that was just right. Now, to test this, they did something really clever. They decided to disguise the bad flames to look like the good one. So they added a little bit of hydrogen to flame A. That hydrogen loves oxygen, so it pulled the oxygen away from the catalyst. Then they added a tiny bit of air to flame C to give its catalyst a little bit of oxygen. The result? It was incredible. Both flames immediately fired up and started churning out nanotubes, just like flame B. This was some seriously strong evidence. So they were close. They were so close. But you know how science works. They needed that final definitive proof. They had to catch that catalyst in the act and figure out exactly what it was. So for the final test, the smoking gun, they used this tiny little probe to sneak in and suck the catalyst particles right out of the successful flame B. And they did this before the particles had a chance to grow any nanotubes. Then they took these pristine little particles and ran them through a furnace under different chemical conditions. And the results were crystal clear. When the particles were in a neutral, inert atmosphere, their size didn't change. But when they added air, oxidizing them, the particles actually got bigger. And when they added hydrogen, reducing them, they shrank. This was it. This was the proof that the catalyst from the magic flame B wasn't pure iron and it wasn't fully rusted iron. It was something in between. So the perfect catalyst, the secret sauce, turned out to be something called an iron suboxide, a perfect chemical balance between pure iron and fully rusted iron oxide. They had done it. Case closed.
So what's the reward for solving such a complex chemical mystery? Well, the payoff was even more spectacular than they could have hoped for.
Over 100 microns per second. That was the growth rate. Just let that number sink in for a second. 100 millionths of a meter every single second. And to really get how fast that is, that's fast enough to grow a nanotube that's 1,000 times longer than it is wide in less than 10 milliseconds. That is literally faster than the blink of an eye. The whole process is happening on this unbelievably fast, efficient timescale. And all this magic happens in this incredibly small, precise location, just a couple of centimeters above the burner. In the flame's exhaust, the nanotubes start to form. Then, in a tiny little 4-millimeter window, the growth just explodes before stopping just as quickly. It's like a perfect microscopic assembly line, just hanging there in midair. So why is this such a big deal? Well, what this research gives us is a recipe for making incredibly pure carbon nanotubes without all the gunk, and you can do it at normal atmospheric pressure, no expensive vacuum chambers or anything. The growth rates are just off the charts, and most importantly, this flame method finally opens up a real path to making this wonder material on an industrial scale. And that kind of brings us to the final thought here. This whole incredible breakthrough came from just carefully looking at and tweaking the chemistry of something as common as a flame. It just makes you wonder, right? What other amazing scientific secrets, what other revolutionary new materials are hiding right there in front of us, just waiting for someone to ask the right question? Thanks for joining me.